Luis Ibanez will tell us about the intersection numbers of the standard model.
Okay, so let me start by giving a short and fast review about the traditional approach to the embedding of the standard model in string theory. The prototype is probably the heterotic weakly coupled E8 cross E8 compactified on some Calabi-Yau or orbifold. That, for example, if we compactify in a 2,2 compactification in a Calabi-Yau, the number of generations is 1/2 the Euler characteristic. All this is well known. What is the present status of this approach? Well, it's some encouraging progress because a number of 3-generation models have been constructed. Not that many, but a number of them. But it's fair to say that at present there is no model yielding just the spectrum of either the standard model or the minimal supersymmetric standard model. Typically what happens is that there are extra unwanted fermions or even gauge interactions like extra U1s, which remain at low energies. Then it is fair to say that as a consequence of this fact, the nice joining of gauge coupling constants in the MSSM has not yet been reproduced in the string context. In all models studied, also the question of proton stability is sort of accidental because it appears as a consequence of choosing some clever direction in charged scalar field space so that you can avoid it. So it's nothing which is that natural. And it doesn't seem that things are going to change if you go to the strongly coupled heterotic. So this approach is really a top-bottom approach. Where you start from a lot of symmetry, large gauge group, and then you do all kind of, you torture the poor manifold so that you get down to what we see. But with the advent of deep brains and related aspects in the last 7 years, so it is obvious that there is an alternative approach to understanding or describing the standard model in this context, which is a bottom-up approach. It is natural to think that, well, why not? Deep brains support the gauge interaction, so here is SU3, here is SU2, here is U1, just some parallel deep brains, okay? So the question is, the obvious question is, can we build a deep brain description of the standard model? What would be the interest of that search? Of course, the unification of gravity and standard model interactions, perhaps also construct the string realization of the brain-well ideas, if you are interested in that, but also to find new avenues to understand mysteries of the standard model, like family triplication, the unreasonable stability of the proton, or even the fermion mass hierarchies. Of course, that's a hope. Of course, the first ingredient in all this is that you have to obtain chiral fermions. That's perhaps the deepest property of the standard model. Fermions are chiral in the standard model. So if you put deep brains on a smooth space, you will get something which is not chiral. So there is a number of ways, and which are not unrelated, in fact, to get chiral fermions in string theory. For example, one of the simplest is to locate deep brains at some singularity, for example, orbifold singularities. But I'm going to concentrate here on something which is, I think, I see as sort of efficient in order to get what we want, which is to reproduce the standard model, which is intersecting deep brains. So this talk is based on work done in collaboration with my students Fernando Marchesano and Cremades, and also Raul Rabadan at CERN, and also with previous work with Uranga, Rabadan, Franco, and Aldasaba. There is important previous work by the Berlin group. And of course, the fact that you get chiral fermion intersection is well known. It was emphasized by these people in a dual, T-dual version, these other people. And in the last year or so, there have been a number of papers related to these intersecting brains. Here, this is a partial list of them. So why intersecting brains? Well, intersecting brains because they have a number of properties which are present in the standard model. To start with the gauge group, each stack of n brains carries a UN gauge group, and the standard model is a unitary group. Also, chirality, two intersecting brains present chiral fermions at their intersections, transforming as bifundamentals. As I will describe in a minute, the quarks and leptons of the standard model can be understood as bifundamental representations of unitary groups. And also family replication, breaks at angles if they are wrapped in a compact space, they may intersect more than once. So, for example, visually, imagine we have a pair of D4 branes with the Bohr volume containing Minkowski and with the other dimension wrapping a 2 torus. Here, for example, is a brane wrapping this direction. Here is another brane in green wrapping 3 times about this direction and 1 in this direction. I will denote with numbers and m the wrapping numbers in one and the first and this E1 direction and the second in the second direction. So this is a brane 1, 0 and the other one is a brane 1, 3. They intersect at 3 points. Okay, so typically in the simplest compact spaces you can think of tori, that will be the origin of replications. So what is the minimal structure in order to obtain what we see? I mean the standard model. What stacks of branes you need? Okay. Before entering into specific models, we need, if you want to get them from B fundamentals, you need a minimum of 4 stacks, which I call baryonic stack, left stack, right stack, and leptonic stack. So the idea is that the baryonic stack, which contains 3 branes giving rise to color, will intersect with the SU2, the left branes, and at the intersection you will get B fundamentals, so left-handed quarks. In order to obtain leptons, you need this leptonic brane. Left-handed leptons will appear in this intersection. And you need a further brane, the right brane. At the intersection of this one with the baryonic brane, you will get the right-handed quarks. And at the intersection of this one with the leptonic one, you will get the right-handed leptons. This is the what we need. Okay. So, but what is the philosophy? The philosophy is that, for example, looking for branes wrapping cycles, giving rise to the intersections that we want, which reproduce the standard model. And that may happen in a variety of compact spaces. Of course, I'm going to concentrate on something simple, which is toroidal. We can consider, for example, D4 branes wrapping one cycle in 1, 2 torus and then being located at a singularity in some other extra dimensions. But most of what I'm going to say, I will concentrate on D6 branes wrapping 3 cycles on T6. This is the simplest example one can think of. Again, before even getting into the details, there is something interesting which you can say concerning something interesting like number of generations and number of colors. There is an important constraint in any deep brane model, not only intersecting models, with fermions in B fundamentals, which is that the number of n plates of UN has to be equal to the number of n bar plates of UN. That's sort of obvious. You want to cancel anomalies, but it is true even for U2 and U1 gauge groups which you have there. So imagine I want to impose that the number of doublets of electroweak doublets is equal to the number of 2 bars of U2. Here makes sense distinguishing 2 plates and 2 bar because there is a U1 there. Now, imagine you say, well, the left-handed quarks are all of them 3,2. They are doublets, not anti-doublets. All together you have 9 doublets. But then that you will be unable to cancel the U2 anomaly because with 3 leptons, at most, the best you can do is to have 3 anti-doublets. So you are missing 6 doublets here. So the minimal standard model in quotations has U2 anomalies. That was telling you that you need 6 extra fermionic doublets to cancel anomalies. And in fact, this was experimentally observed in the last 3 years. When people constructed deep brane models at singularities, there was always 6 extra doublets. We should have realized that it is obvious. It's just a question of canceling anomalies. But there is a simple way to cancel those U2 anomalies if the number of generations coincides with the number of colors, which is that 2 of the left-handed quarks can be doublets and the other one anti-doublet. Then you have 3 net doublets and 3 net anti-doublets, and they nicely cancel. So this is important in order to reproduce just the standard model spectrum without extra doublets and things. Okay, but that means that we will need 2 kinds of fundamentals, or B fundamentals of this type, NM, and B fundamentals of type NM bar. So where can you find this kind of B fundamentals? In string theory, they appear naturally in orientifolds. So what you do is you mold out type 2 string theory by the world sheet transformation and by some geometric reflection, typically. Now you have a configuration of this type. You will have to add, apart from your branes, a mirror brane, which is just a reflection under omega r. So what happens if you have a brane D, A, and B, at the intersection you will get a usual fundamental, n bar. But at the intersection of a brane and the mirror of the previous one, you will get n comma m. So you get the two type of B fundamentals you're interested in. So we need orientifals to really reproduce the minimal standard model content. So what are, with this simple configuration, you can already know what we want. We want 3 copies of all quarks and leptons, except for the left-handed quark, which you have one of one type with charge -1 and 2 with charge +1. These are the charges under the 4 U1s you have here, which are fixed in a model-independent way. By the way, you have to add necessarily a right-handed neutrino here if you want to cancel the U1 anomalies. So indeed, the gauge group apparently is SU3 cos SU2 plus 4 U1s, but we will see in a minute that generically there is only one massless U1, the other one gets massive. So let me be now a bit more specific and consider this is branes wrapping at angles on a 6 torus, and consider a factorized 6 torus, and then the 6th brane is, includes Minkowski space and is wrapping in a factorized manner, a cycle in each torus. So here we have a red brane intersecting a blue brane with intersection number, in this case is 2 times 2, is 4. The intersection number in each, the total intersection number is the product of the individual intersection numbers in the tori, and each individual one is given by nm minus mn, something which you can compute. Now you do, as I said, you have to do an orientival of this construction in order to get both types of B fundamentals. So you model your theory by omega and r, where r is the reflection with respect to the 3 of the compact dimensions, each in a different torus. Then, well, due to this, for the projection to be consistent, the lattice has to be fixed either to be a square or tilted. And the other consequence is, as I said, that you have to add mirror branes in the construction. So what is the fermionic spectrum? In each brane will carry initially an n equals 4 supersymmetric multiplet, but then you will have, as I said, intersections of a brane A with the brane B giving B fundamentals one type, and with the mirror one B fundamentals of the other type, and they will be multiplied by the corresponding intersection numbers. Now, in this kind of construction, of course, you have to impose the cancellation of Raman tadpoles, which will guarantee for you also the cancellation of non-abelian anomalies, and what I told you before, that the number of fundamentals and antifundamentals are the same. And in the present case, the conditions are these conditions on the different wrapping numbers of each stack on the 3 tori, and this 16 here appears because we have an orientival. So, okay, so what do we want to get? This is what we want to get, what I call the standard model intersection numbers. So I recall A is the baryonic U3 stack, B is the U2 left stack, C is the right stack, and U1 and D is the leptonic stack. So we want intersections 1 and 2 to get the left-handed quarks. Here, those are the intersections corresponding to the right-handed quarks. This will be the left-handed leptons and the right-handed leptons. So what we have to do is to look for choices of wrapping numbers along the 3 tori, yielding the fermion spectrum of the standard model that we displayed before. And there is a general solution. Here is the general solution. This is the 4 stacks, okay? And these are the wrapping numbers in the 3 tori. So here the solutions depend on 4 integers here, and B and C and A and D here, and well, some other discrete parameters. So all of these wrapping numbers are going to give a massless spectrum, which is just the one of the standard model. It is interesting that once you impose that you get the standard model spectrum, then automatically 3 of the tadpole cancellation conditions are automatically satisfied. It's not that surprising. We know the standard model is anomaly free, and that tadpole cancellation conditions are related to anomaly cancellation. So that's what's going on. But still, there is a tadpole condition which must be fulfilled, and it's very easy to fulfill for a lot of choices of these discrete parameters. Particularly interesting in these constructions are the UNsymmetries. This is again the spectrum of the standard model plus right-handed neutrino. And these are the model-independent charges of under the U1s of the quarks and leptons. There are 4 U1s, 1 per stack, but all of them have familiar interpretations. The U1 of the baryonic stack is baryon number. The U1 of the leptonic stack is lepton number. Then there is 2 other U1s, one which can be identified with right-handed weak isospin. There is another one which is a sort of Pechequin symmetry. So in this context, these non-global symmetries of the standard model are in fact gauge symmetries. There are 2 which are anomaly-free. This combination coincides with B minus L, which is known to be anomaly-free in the presence of a right-handed neutrino. And QC is nothing but the right-handed weak isospin of left-right symmetric models. This linear combination, of course, is the familiar hypercharge. There are 2 which are anomalies, and they are model-independent. They are always the same combinations which are appearing and are anomalous. These anomalies are cancelled by a generalized Green's-Bass mechanism, which I described now briefly. In this theory, we have Ramon-Ramon 2 forms, which are obtained by wrapping the Ramon-Ramon 5 form on 3 cycles in the tori. In fact, 4 of them are relevant for this cancellation of anomalies only. What happens is that all of the U1s have couplings, genetic couplings to those Ramon-Ramon forms, couplings of the form BF, and the dual axions are coupled also to the abelian and non-abelian gauge groups, so that you can check that the sum of the contribution to the anomaly of this in the usual triangle graphs adds up to 0. If a U1 is anomalous, of course, necessarily there must be a BF coupling, so that this mechanism is proceeding. But BF coupling can be seen to, what it does is to give a Stuckelberg mass to the U1. So all anomalous U1s are massive automatically. So the 2 anomalous U1s are massive. But not the other way around. I mean, there are also BF couplings which can give masses to some anomaly-free U1s. I have to emphasize that even the abelian gauge symmetry is lost because the U1s, for example, the anomalous U1s became massive. They remain as perturbative global symmetries. There is no scalar here getting a web, so the U1s remain as accidental global symmetries. Concerning the 2 anomaly-free U1s, there is always one linear combination which is massless, which means that it doesn't couple, it doesn't have any BF coupling, which is this particular linear combination in terms of the wrapping numbers and the parameters of the solutions. And whenever a certain condition is obeyed, it is the hypercharge which remains massless, and the other anomaly-free U1 becomes massive. So altogether, when the dust settles, we have the spectrum of just the standard model with 3 generations. The gauge group is just SU3 cos U2 cos U1, no exotics, no anything. Talking about the non-supersymmetric standard model all the time, which is nice. What about scalars? There are also scalars at Disiss-Brain intersections, which you can call, if you wish, quarks and leptons. And the lightest of them have these masses in terms of the relative angles in the 3 tori of the given intersection. And for wide ranges of the parameters, those scalars are non-tachyonic. So the open string sector is stable. Interestingly enough, for particular choices of the radia and wrapping numbers, there is a massless scalar at the intersection, which is signaling the presence of n equals 1 supersymmetry at that intersection. However, a fully n equals 1 supersymmetric toroidal Brane configuration cannot be obtained by tuning the radial because, well, it is really essentially forbidden by Ramon-Ramon tadpole cancellations. Other groups, particularly Uranga, Svetic, and Xu, have constructed models which are supersymmetric. However, they do not have only B fundamentals, so the model has some exotics. But I'm sure somebody will build soon some n equals 1 version of this. Another point is that one can obtain some interesting models in this construction, toroidal construction, in which all intersections respect some supersymmetry, but not the same. This is easy and natural. This is something I call here quasi-supersymmetric or pseudo-supersymmetric models. For example, a subset of the solution of those wrapping numbers for particular choices of the radii are such that the left-handed quarks have respect one supersymmetry, the right-handed one's a different one, the left-handed lepton a different one, and the right-handed lepton a different one. So it's what is interesting about this is that the quantum corrections for the masses of the scalars in this class of theory appear only at 2 loops, which can be interesting perhaps in order to stabilize moderately the hierarchy. Of course, an obvious question is, can we get also the spectrum of the MSSM? The important point in the MSSM is that now we have also a Higgs sinus. So there are extra fermions. So it is different intersection numbers that we have to obtain. And the answer to that question is yes. Here there is an example of 4 stacks, again, with these wrapping numbers. You get this spectrum, which is that of the MSSM plus right-handed neutrinos. If a particular choice of the radii, for the ratios of the radii are chosen. But I repeat again, for this particular toroidal model, this is not really any one supersymmetric, because necessarily to cancel tuples, you have to add other sectors which are not going to respect fully supersymmetry. Well, I must add that while imposing supersymmetry in this particular model, it turns out that there is, in this case, an additional U1B minus L which remains massless. It's not clear to me why that's the case, but that happens. Just a comment about the Higgs mechanism in this context. Everybody is familiar to the Higgsing which occurs when you have a stack of branes and you separate some of them. That corresponds to a joint Higgsing, but that's not what we want for the standard model. If we were interested in having a sort of D-brane description of that kind of breaking, it rather looks like a brane recombination process, which would correspond to the following. In fact, imagine we have 2 branes which intersect at some point. Varying the radii, you can get a tachyonic scalar here. The scalars which we have, some of them can become tachyonic. That signals that the configuration is going to be unstable. What will happen is that these 2 branes will fuse into a single one, and that if you started with 2 U1s, you end up with 1 U1, so you are lowering the rank. So that should be the, in quotations, D-brane interpretation of Higgs mechanism which lowers the rank. Let me comment about, in this context, a possible origin for hierarchical Yukawa couplings. In these models, the Yukawa couplings, of course, come from correlators for the quarks, from left-handed quarks, right-handed quarks, and Higgs fields. And the world sheet is a triangle, okay? Now, but different generations are going to be coupled to the Higgs with triangles of different sizes. Now, the Yukawa, you expect that for moderately large radii are exponentially suppressed in this way, exponential to minus the area of this world sheet. After brane recombination, still there will be some area left there, which will can explain the presence of small Yukawa couplings and masses. So here is a qualitative description of what could happen. This is 6 fundamental regions of a 2 torus. And imagine we have the Higgs field in here, which comes at the intersection of the left stack and the right stack. And this is the baryonic brane. Okay? Now, if at the intersections which lie closest to the Higgs, you would assign the top quark, because then the triangle is smaller, and the Yukawa coupling would have less reduction. And the charm would be more suppressed, and the other family would be more suppressed. So this is a natural mechanism to obtain hierarchical Yukawa couplings. In the particular toroidal models I was discussing, these models are non-supersymmetric, so there is a hierarchy problem in general. So we better have, for example, one possible solution, perhaps not the only one, is to lower the string scale down to 1 TeV. So in order to do that, what you do is to have some extra dimensions and making them as large as you can. In the case of the toroidal case, you cannot, there is not a direction which is transverse to all the interesting branes at the same time. So that thing does not automatically work. But certainly in other, in Calabi-Yaos or in other configurations, that will be the case. Alternatively, you can use lower dimensional branes, like 5 branes, which do have transverse volume, so that you can reduce the Planck scale. And then you can construct D5 brane models in which you again obtain the same intersection numbers of the standard model. What about gauge coupling constants? Well, the gauge coupling constants are given by the inverse of the volume each brane is wrapping. So in this context, the SU3, the strong interactions, are stronger than the weak interactions because the baryonic branes wrap less volume than the left branes. There is no unification of coupling constants in here in any place. On the other hand, the U1 couplings are related to the non-abelian ones. So let me make a small comment about gauge coupling unification. We all love this thing, and this is the transparency you give in popular talks. Then I have shown this plot many times for popular audiences. In the minimal MSSM, couplings unify nicely. However, do not forget that up to now, I repeat, nobody has constructed a string compactification in which the MSSM unification takes place. So perhaps nature has been perverse, and this is a false track. So let me make a joke. This is the sun, isn't it? And this is the moon. From time to time, this happens. Okay. So there is a perfect unification of the apparent size of the sun and the moon. Okay. So, you know, upon this thing, there have been a lot of theological discussions about, you know, male and female, positive and negative. So perhaps we are doing the same thing, whereas the real answer is that it was just a coincidence on how, you know, whoever cheats once, nature did it, may cheat twice. So since Mike is there pressing me, I will skip and almost directly go to the conclusion. Just a comment on baryon lepton number violation. Baryon number is a gauge symmetry here, so the proton is stable. Okay, whereas lepton number may or may not be broken depending on whether the right-handed neutrinos get a BEP or not. So that if it's not the case, then neutrinos would be only Dirac. So the conclusions is that I must emphasize that this is what I believe is that this is the right language to address the problem of finding the spectrum of the standard model in string theory. We've seen that not necessarily in tori, but in more complicated Calabi-Yaos or whatever. We have seen that things like chirality, family triplication, and proton stability have an explanation in this scheme, and that some things like hierarchical Yukawas or the size of gauge coupling have also geometrical interpretation in this language. We have seen that with this language you can construct for the first time, do a bottom map. For the first time you can at least to obtain a brane configuration whose Marley spectrum is just the standard model and nothing else. I must emphasize that the standard model intersection numbers are topological in character and may appear in general deep brane configurations wrapping Calabi-Yau compactifications. Okay? But of course, there are a number of things which I have skipped, which are the difficult ones. In particular, the stability of the configurations. The model discals are non-SUSY and generically have Nevers-Bartat poles. So it would be interesting to look for stabilized vacua, perhaps with, like Kapru was mentioning, with some antisymmetric tensor fluxes, or perhaps even going to N=1 models, although that's complicated, but in principle possible. Another interesting point is to go and construct fine models in Calabi-Yau compactifications with cycles such that the intersection numbers of the standard model are reproduced. So in one word, what I'm saying, instead of looking for Euler characteristic 6, we have to look for intersection matrices given the standard model as I showed you. Thank you.
Questions? Paul.
You had the nice argument about the number of colors equaling the number of generations.
Yes.
but it looked as if one of the three quark generations is asymmetric with respect to the other two. It's a
Yeah.
2-bar instead of a 2.
Yeah, but the U1 is massive.
So, but
The U1 is massive because it mixes with this Ramon tensor, so it has really no effect. There is no violation of universality for any practical purposes.
You don't have to choose one of the three families to be the asymmetric one. Is that what you're saying?
I don't know which one is the asymmetric one. Maybe the top quark, that I don't know yet. I mean, you need to know the details of the fermion spectrum.
Other questions?
If neutrinos have Dirac masses, roughly how big would they be?
Masses, Dirac masses.
Yes.
If lepton symmetry is not broken, then the neutrino had to be Dirac. Then, I don't know, but they, in principle, they can be suppressed, exponentially suppressed by the kind of well-sheet diagram, triangle diagram that I showed to you. I mean, you have to produce, in that case, a model in which all the U-kappa couplings are exponentially suppressed more than the usual quarks and leptons. So that, but
And if
I
they are
cannot tell you.
Majorana masses, what would they be?
Sorry?
How about if they are Majorana masses?
The Majorana masses normally will be of the order of a string scale. So if that's the case, then you should put up your string scale up to at least 10 to the 10 or higher scale in order to fit the observed data.
Other questions? Okay, well, I have questions, but I'll be a good chair and save them for the break. And let's thank the speaker again.